After the knowledge engineering process, we should have a planning domain and maybe planning problems that we can give to a planner as input. The planner then does the plan generation, and that's what we've looked at so far in this course, algorithms that synthesize plans. But the algorithms we have looked at make some assumptions which may not hold in the planning problems we are trying to solve. I will now try to give you an overview of some other issues and problems that may come up during plan generation and how those can be addressed. Before we talk about different types of planning problem, here's another approach to the planning problem as we've described it so far. Up to now, we have looked at planning algorithms that take a planning problem, apply some algorithm, and the result is some plan that is a solution to the planning problem. Another way to solve planning problems, the same planning problems, is to transform the problem into a different type of problem as a first solution step. And in this approach here, the problem we transform it to is a SAT problem, a satisfiability problem. I'm not going to describe the details how this is done here. But SAT problems have been around for a long time, and in fact 3-SAT was the first problem to be proved NP-complete. So there are a number of efficient solvers that we can use to solve SAT problems, and what they give us is a SAT solution, which is an assignment of truth values to propositional variables in the SAT problem. And given such a SAT solution, it is fairly easy to extract a plan from this solution. So you can see this approach is quite different from everything we've seen previously because it doesn't tackle the problem head-on, but transforms it into a different problem, solves that problem, and extracts the solution from that other solution. And the main reason why this approach works so well is, of course, that we have efficient SAT solvers. This approach was quite successful in the mid to late 90s, and the planner that implemented it was called Black Box. All the planning algorithms we've looked at so far deal with planning problems where the actions are deterministic. That means if we apply an applicable action in a given state, we end up in exactly one other state, and that state is known. However, there are many problems where the outcome of actions is uncertain. And if the outcome of an action is uncertain, that means after we apply this action, we don't know exactly which state we are in. So the state we are in is also uncertain. Now, there are at least two different ways in which this type of uncertainty can be dealt with. The first approach is called belief state search. And our search space in this approach is a state of belief states, where each belief state is really a set of world states. And we know that only one of these states is the actual states, but we don't know which one, but we know it is one of them. So that's what we call a belief state. It's a set of world states. Then, when we apply an action in a belief state, of course the outcome is the union of all the successors of the individual states. So again, it's a belief state, a set of world states. So this gives us a search space as we've seen it before, and the result then is a solution plan, which is a sequence of actions as we had before. Another approach to dealing with uncertainty is called contingency planning. In contingency planning, what we have is actions that have multiple possible outcomes, and these action outcomes are known as contingencies. Usually, the number of contingencies is fairly small, and not every action must have contingencies. So that means when we search through our search space, we can still deal with individual world sets. But now our solution plan has a tree structure that branches where we have to take into account the different contingencies. And also our solution plan will contain observation actions at the branching points where we, during execution, observe which of the branches is actually happening. Of course, both these approaches are a lot more complex than what we've seen so far. In belief state search, we have sets of world states as our nodes, so an exponential increase in the size of the search space. And in contingency planning, we look at plans that are trees, so they are also a lot larger than the plans we've looked at so far. Sometimes the degree of uncertainty that we have on a planning problem can be quantified. That is, we know with which probabilities the different outcomes of an action can occur. This approach is called probabilistic planning and is based on a different conceptual model. So we're no longer looking at simple state transition systems as we have so far, but the new conceptual model is called a partially observable Markov decision process, this one here. And in this model, we have a lot of familiar things. So firstly, we have a set of world states through which we are searching. And then we have a set of actions that give us our state transitions. And of course, in some sets, certain actions are applicable, and they must be a subset of all the actions that are available. What we also have is a cost function that gives the cost of an action applied in a given state, and this cost must be greater than 0. So far, this should all look familiar. But then, in addition to all this, we have the transition probabilities. That is, we have a function that gives us the probability for each action that we end up in state S prime, given that we started in state S. So this is the probability that we get from S to S prime when we execute the action A. Then our planning problem also must include an initial belief state. That is a probability distribution over all the states in S. So we don't know exactly which state we start in, but we have a probability distribution that tells us how likely it is that we are in a given state. And we have a final belief state which corresponds to our goal. Now, the solutions to our probabilistic planning problems look quite different from what we've seen so far. They are no longer action sequences, but they are something known as a policy. A policy is effectively a function that maps states into actions. Namely, if we are in a given state, that's the action we should execute. That most likely leads us to a goal state. And often the policy we're looking for is an optimal policy, which is simply one that has a minimal expected cost.